And what I'm going to speak about is my experience I have in the wind tunnel at the von Karman Institute, and what I think should be their future needs, at least part of it. How do I switch? Okay, so at the VKI we have the VKI L1B wind tunnel, and we can create different roughness, offshore roughness. You see there, if you put little cups, we have rural roughness, and we can simulate even the city if you put big coffee cups upside down, and then we need some transition blocks to go to the turntable. And because of this transition, we still have 10% variability on the mean velocity and turbulence intensity on the turntable, and that's exactly the same problem you have at the CFD. I want to skip the next slide, but no one showed it yet. There are two religions for the atmospheric boundary layer. One is the Locke law, where of course, the roughness length is very important, which should be about 1/10 of the physical height of the cups. And the other religion is the power law, where you have the shear, the exponent there, which is doing the job. Actually, if you plot both of them, you see, obviously, they speak about the same thing as it should. So Erwin described how to do it. So you put fans or spikes, and that controls the boundary layer height, and also gives you turbulence in the outer layer. This should match, of course, the turbulence that is created by the inner layer, and that's done by these cups that I've just shown. Already Cunningham in 1967, if I'm right, when it's written there, he said, well, this is how it should be, the relationship between the two religions, so the power exponent and the roughness length. And he made this fit to it, and you see the higher you go, the more urban you become. Now, if we put the fit to our wind tunnel data, of course it doesn't fit. Our wind tunnel is much smaller than reality, so it's actually, it doesn't fit at all. And actually this allows us to find, if I shift these curves there, this allows me to determine the possible range of scales I can put in my wind tunnel. At VKI we have different possibilities of cups and spikes, and you see here all the possible ranges we can do. What is very interesting, in fact, is the offshore case. No roughness, just a long fetch of a flat plate, so no transition problems. I really like that one, because you don't have the transition problems, but also because you can shift it over a long range of scales, from 1 to 25 to 1 to 6,600. And this is one of the reasons why I like very much offshore conditions. For CFD, of course, it's fantastic. You just put the same thing as in the CFD, and you have no transition problems. I looked on the website of Ted, and he also likes offshore conditions. Here he put his, I think must be Montreal, at sea conditions. There are clear reasons to do this. It could be that it was wind loading study, and then the offshore conditions is a safe thing. But this afternoon, you will probably speak more about why you put Montreal in the sea. At VKI we have a closed wind tunnel. It's there since 1950. Originally it was there to measure the forces on rockets, on airplanes, and we still do that. But since the 80s we have one additional test section, the rectangle wind engineering test section, with one turntable on the front, more for vehicle aerodynamics, and one on the back to put cities. Here you see a picture of it, and there's the turntable in the back. Now, wind turbines are very popular, and you can detect in one shot the regions in a mountain range where you have to put your wind turbines. So this is, I don't know if you know it, Alice Mountain, close to Pamplona in Spain. They're on a high plateau, they want to put it. There's a plane in front. Here I'm standing on the plateau, and there's a picture of the ridge which is there. And of course, when you have such a project, always the question, should we include this ridge or not? Many people didn't. We decided to do it. So what you see here is the wind tunnel model, 15 by 15 kilometers. So obviously we didn't have to put any roughness there. So it was 1 to 5,000 the scale. And we worked for 9 months. We scanned with PIV, with LDV, with hot wire, all the velocity fields to know where to put the wind turbines, and obviously to create benchmark cases for CFD people. And then during one coffee break, I said, come there. We put sand everywhere, and here you see the model completely put to sand, and 15 minutes, coffee breaks are a bit shorter at VKI than here, and here you see some pictures. The little ridge is there, here's the high plateau, and at low wind speed, when you have sand erosion, then, you see it here, can I stop it? No? Voilà. You see on the plateau indeed all the regions where you can put the wind turbines, and there are many of them. Actually, there are on all the ridges. It's nice now to go further, let it just play, and look to the ridge there. Oh, okay. Play it again. This ridge had a huge effect on the wind field there, really huge. In CFD we found even that the sharpness of the ridge was completely determining, it's not, I cannot see it, is it going? It only wants to play once. No, there it's going. So there was a natural park, so they couldn't put anything, but also there where they're going to put, actually it worked very well. There's the ridge. Sand remains there until the end of the test, which is at very high wind speed. So I said already that the details of the ridge are very important. Actually, I learned that from Ted. He mentioned that when I was giving a presentation in Brussels during the COST C14. You mentioned the details are so important. So that's why I put this ridge. Thanks to you. So actually I was looking to this. Look to the wind comfort you have there. It's fantastic on the leeward side of the ridge. So I looked on Google Maps and I saw actually that villages are aligned on that side. They are looking for good wind comfort and not for water. The water is definitely running in the valley there. So that's funny that people need better wind comfort than water. You can actually come up with fraction speed up ratios based on sand erosion. Blue regions, good wind comfort. And the red regions is where you have to put the turbines. I said already, now we master very well to do these PIV measurements. This is the fraction speed up at 90 meters. Red is PIV, and the other curves are CFD. I think the wind tunnel case we can master very well because they are neutral atmospheric boundary conditions. If you go to non-neutral conditions, that means the field data, it doesn't fit at all. This is CFD, this is experimental. They are not along the line. There are a lot of outliers. And CENER, the Center of Renewable Energy in Spain, attributes this to the fact that there is never a neutral condition in this mountain, they say. So that's a real problem. And you can, and I think that's one of the things I want to stress. I put here, you have to go to this website, it's fantastic. You can simulate the atmospheric boundary layer and the effect of the temperature very well. There's a nice movie there done by the University of Minnesota by Fernando Portajal. There are two snapshots I took, one during day, the one in the early morning. This is vertical cuts, this is velocity temperature. You see here it's quite uniform. Maybe you can put a log law approximation at the lower part, but definitely here you will enter in trouble. So in the early morning, you see this red layer. That's the so-called low-level jet, which is an increase of velocity, which is due to the fact that your temperature is increasing with high, which gives a stable condition close to the ground because of the cooling of the ground. Now this we have been involved in. We have been working with DIWI, which is a German wind energy center that have different masts in the North Sea. Fino 1 is the oldest one, where they have a very long series that you can work with. Actually, we did it with PhD students, so it's a mast of 100 meters, sonic animators. Also, they put one LiDAR scan that goes up much higher to 250 meters, and indeed, it's there. It's there. This is a mean of a long period, because it's not only diurnal effect. You have it during summer, during spring. You actually have it now all the time. The water is still cold, warm air is coming in. This gives stable conditions, and these low-level jets. Who cares? Well, these people. people that put now wind farms inside the North Sea. The first one got more wind energy than they predicted. Well, that's fantastic news. They wanted to understand why, and this mass case is due to stable conditions they have all the time there. So there is a real need for doing this also wind tunnel to get, let's say, low-cost validation, because putting, of course, measurements on sea is very expensive. So who can do that? I think in Europe, not many. I put this one, University of Surrey. They have this wind tunnel where they have heat plates, cold plates, to put the temperature gradient as they want inside their wind tunnel. And already the first wind farms have been studied at stable, unstable conditions in this wind tunnel. I know there is one in Japan, a stable boundary layer wind tunnel, and I think there is a new one coming up in Switzerland at EPFL. At VKI we try a low-cost solution. We have 3 atmospheric boundary layer wind tunnels. One is this one where we can put rain inside, and it's we suck the air out by means of supersonic ejectors. There are no rotating parts, so we are busy now. We didn't succeed very well to put a cold gas cloud of until -50 through a porous floor, and like that we hope to be able to create a neutral atmospheric boundary layer. This is really a need for the future for atmospheric boundary layer wind tunnels. It goes even further, because when you have stable conditions, okay, this is the standard profile, and the Ekman layer is high up. We don't care about the Ekman layer, but yet we have to do. The Ekman layer is coming down. It's going down when you have stable conditions. Ekman layer, it means you have a balance between the Coriolis force and the eddy viscosity, so the friction at the floor. In fact, when you have stable conditions, your integral length scale becomes very small, your eddy viscosity becomes very small, and your turning of the wind speed with altitude happens already in the first 100, 200 meters. A fantastic simulation you have here again from Portage, which shows that the wake of a turbine is much affected, again over the North Sea, when you have this Ekman turning. It's important when you plan a whole wind farm. So now I have a question to the audience. Who knows how to do Ekman turbine in the wind tunnel? Is that possible? A wind turbine is a tube with a ventilator. How can you do the twisting? Does it exist? Somebody knows it? Actually, yes, it does exist. I recently discovered it. I found it really funny. It's in New Zealand they do it. Look, it's a standard wind tunnel, a fan. They have the blocks, and just before the turntable, they have these flow twisting vanes. It's not to have the Ekman layer. It's because you go with the yacht through the atmospheric boundary layer, your apparent wind direction will change with height. And if you don't have this horizontal twist inside, you will not get your forces correct, you will not have your sail correct, and you will not win the race. Now, of course, what I'm interested in, that those people get rid of this boat and put this inside. So this is the Kingdom Tower in Saudi Arabia, soon to be the tallest tower. I would like to see the effect of the Ekman turning on the torsion on this building. And with that I would like to finish. Thank you very much.